Welcome, welcome everyone. Very good day, very peaceful spring day, and welcome to the stream. We are going today to work on, say, Go runtime and pick up some work that we started on stream back in February. So there is this RFC here that was describing the various experiments we were running, and that suggests to create a new task group abstraction inside the Go runtime and then attach some properties to it. And we were pretty successful back then creating some way to track CPU time and utilization per task group in a way that's relatively precise, and that was nice. But we were not actually successful in looking at a heap usage properly. And so the main reason why this was an issue is because the Go heap allocator has two different levels, and we didn't know what to do with the small level, which is shared across threads and Go routines. And so back then we didn't really do anything with this. And so it's going to be today's experiment to try to at least count allocations and then try to get a deallocation counter for, say, large allocations. So we are going to try to introduce two allocation counters, one for small allocations, one for large allocations, and then a deallocation counter for the large allocations. And we are going to verify that the deallocation tracks the allocations so that we are not leaking values in the counter. So we're going to resume work using the branch that I was working on back in the days, but we do need to find where our repository is, and I think that is this one. And so we need to fetch that branch because I think it's not there anymore. Yes. All right. So there's CRDB fixes and task group. So task group is off the 1.16 beta 1 tag in the Go repository. So we are going to want to rebase this work to, oh, it's already off the 1.16 here. So this is task group, and then task group, then task group, and then task group. So, okay, so we are going to work this branch and we need to rebase it to the latest Go 1.16 release, which I think is going to use 1.16.5. Okay. Let's see if we can rebase this. All right. What am I doing? This does not sound right. This does not sound right at all. Why do I not see? Why do I not see my rebase? Oh, because I'm not on the branch. That's why. All right. That sounds better. All right, so fingers crossed this rebase is clean. Not much has changed. that sounds right. And now we want to build this. I don't remember how building works in this. I think there is a in the source directory there is a build all or make. I don't need build all. I only want the one for Linux, I think. All right, so if this builds, we're going to refresh the branch on the remote repository, like on our fork, and then we're going to move forward with some heap instrumentation. Yeah, that seems to be fine. All right, that is great. That seems to be completely fine. And then there is a branch for CockroachDB that uses this runtime. So we are going to use this branch. Oops. For CockroachDB to verify that it still builds properly. And so we will need to rebase that. Yep. Some conflict. Let's fix those conflicts. All right, so let's skip this. And we need to regenerate, say, the code, so it's generated code. All right, so this is failing as expected because I just tried a build using the standard Go runtime and we need the features from the new one for this experiment. So the way I'm going to do this is export. And like this. And then we can try again. Cool. So that builds. All right, so our rebase here seems to have succeeded. And so we're going to complete the rebase and then push to upstream here. And this has succeeded into building something, and so we are going to push this to upstream here. Cool. And now we can go and explore the Go runtime system. So to do this, we will need to rememorate a little bit what we were working with last time. So of course, all this is experimental, so we're looking at code that's not exactly living in the right places, and so arguably we will be moving files around and creating APIs that can be used, or like that ensures that the CockroachDB executables or any program that wants to use these new features can be built with a regular Go runtime without the fixes. So we want to have them in a way that can be adopted organically. So that will come later. But until then, we can work with this experimental repository structure. And so let's rememorize, reminisce what was working last time. So a task group is implemented internally using a T struct, currently with just those counters for scheduling ticks and the CPU times, the exact CPU time. And then separately from this, we also have a separate struct that is visible from Go that enables a Go program to extract metrics, a copy of the metrics into a data structure based on a path. So this makes it possible for Go programs to observe the values maintained inside the runtime without needing to have a public struct definition. And why people would want to do that is this way it's possible for the runtime to change the implementation, the layout of the structs without having to modify all the Go programs that access those values. The path to accessing the values is defined using strings. And I think inside CockroachDB we have a view of this. Let me search for it. Where would that be? In SQL, I think. CRDB internal. Here. Yeah, so here is an example of how those metrics are being read. The metrics package, it's a pseudo package inside the Go runtime, has this public function, and you give it a task group object, which is like an opaque reference, and then the set of sample names you want to poll, and it will populate this array of this slice of metric.sample with values. So like each sample is a combination of a name together with a value. And so the read task group function will populate for each of the elements in that slice the current value of the metric in the value field. So that's what we're looking at. So this is implemented here. We see here same acquire, same release, because we want to prevent concurrent access to the metrics map here, I believe. Yes, that looks right. That is only done once for all the metrics. Where is this? Task group metrics. Oh, here is this one here. All right. And inside the accessors for those various metrics, we have atomic loads so that we don't need to lock the task group separately. So all this logic here has been implemented last time, and it's currently integrated inside the scheduler, the Go scheduler, that is. I don't remember what that is, but we are going to discover it because we know that we were doing this by accessing the nanos fields in the task group inside the runtime system. So is it in runtime and somewhere else? I don't remember, but maybe we can use the referrers. Yes, here. No. All right, I don't remember how this works. Let's look at the Git log. All right, So it's here, all right, in proc.go. So every time we leave a Go routine, we remember the time slice in the .nanos field. And every time we enter a Go routine, we remember the moment where we entered control for that Go routine in these fields. And so we only account for the time, execution time at the end of the time slice. So there was a comment about this in the RFC saying, well, do we really want to have just one time accounting field per task group? Because if there are Go routines for the same task groups running on different processors, and there are many processors, this is going to become a hotspot in the hardware memory system. And that is very true, in fact. That means that something good we can do at this point is to add a comment to annotate this in two places, where this is used here. Explore to see if we need multiple counters side by side to avoid false aliasing. All right. If people who are looking at this don't know what false aliasing is, let's pull up Wikipedia. Or Quora in this case. No, that's not. Quora is the better one here. Oops, doesn't work. So that's probably good enough. So false aliasing is when different physical counters or well, actually, that's not false aliasing. That's actually real aliasing. Okay, never mind. It's not false aliasing. That's actually wrong. Contention. All right, never mind. This was a brain fart. This is not false aliasing. False aliasing would be a completely different area. And so we are going to take this here. And so we have here the same comments here. And we are going now to add these comments here too. All right. This is like performance optimization. If that is necessary, we can make it happen. It's not too complicated. But for the purpose of experimentation, I would say this is premature optimization. So we can look at it later. Give me a sec, I need some water. Cool. All right. So this continues to work the way it worked before. And so what we're going to do today is look at the memory allocator. I don't remember in which file that is, mgc.go of m something. It's in m something. I don't remember which m. So malloc. There we go. All right, so there is a very nice explanatory comment at the top of this file that explains how this works. And what it explains here is that we have small objects being allocated using pages that are shared across multiple Go routines. And then if, say, small and medium cache don't work, then there will be a new group of pages to allocate for that allocation. So like if you remember like memory allocation, you have the Go runtime allocates from the operating system for the process. So the process that needs to allocate will request memory to the Go runtime will do its like cooking, and then if there is not enough memory available inside the Go runtime, then it will go and request more from the operating system. And so we will want today to focus primarily on large objects, because when large objects require obtain a allocation that is dedicated. It's not shared. It's not sharing pages across multiple Go routines, and therefore we have a higher chance to make precise allocations. So there is a little bit of studying, but generally what we are expecting is that there will be an algorithm that that looks at the arguments of an allocation. So everything in the Go programs will start in the function called malloc.gc. That is the entry point for all heap allocations. And so the compiler, the Go compiler, creates calls to this function internally to the code. So programmers don't typically use that. It's not an exported function. And then the compiler passes the size, the type, the data type. The data type is needed for reasons. Might need to look into it later. And need 0 indicates whether the allocation should also make extra work to erase whatever data was present in there. And so what do we see here? So we see here a assertion. This is checks that malloc.gc is not being called while the garbage collector is currently cleaning up. Then if the size is 0, then we are always seeing a pointer to a very particular value, like all the dynamic allocations for 0 size objects, and we have plenty of those, like all the empty structs, will get a address in memory that's all the same, and that makes it possible to avoid allocating 0 size objects, and so it's like generally reduces memory usage for code that uses very small structures. Then we have some debugging, and that is something I've never seen before. So let's see what this is doing then. Okay, so if we are doing malloc debugging and the sbrk flag is set, then we are going to use apparently a sbrk based allocation. All right, I understand. Okay, so that is like a mechanism that bypasses the Go runtime to a large extent, and those row allocations from the operating system. That's pretty nice, actually. Maybe, well, I'm not going to look into this. All right, then we have an assistance. So this is a mechanism that makes it possible to react to memory pressure by one Go routine. If a Go routine seems to allocate a lot, then the garbage collector is probably going to work extra to remove data that was allocated by this Go routine. Let's see what GC assist alloc does. Oops. It is in here. So what does this do? Oh, basically it is forcing. So if the Go routine happens to have as allocated a lot recently, we are forcing a round of garbage collection that makes it possible perhaps to reclaim memory, so that the process doesn't run out of memory if the Go routine is a bit too active with memory allocations. All right. Then we are setting a flag called mallocing, and that ensures that the garbage collector is not going to run during the memory allocation operation. That's an interlock because we don't want to have the garbage collector being confused by the intermediate steps that the allocation function is going to create into data structures. All right, and then we are looking at the mcache. So this is like just retrieval metadata. We're ensuring that there is mcache to work with. And now we're going to to enter the allocation proper. So, as I explained earlier, we have multiple modes. So if the allocation is small, we're going to go through the tiny allocators, the medium allocator, and so on, and everything beyond. Everything before the medium allocator is shared across Go routines, and it uses pages that are shared across Go routines. And we had an issue with our task group abstraction, because if we want to do accounting precisely, those objects will only get released at once in one go by the garbage collector. And so it will be very prohibitive, cost prohibitive, to annotate every single allocation with an additional pointer or reference to a task group next to it. And we don't want to do that. But at the same time, because those allocations are grouped across Go routines, they might be grouped across task groups as well. And so the garbage collector, when it will mark all the objects that belong to small allocations as free, when the entire page becomes reusable, the garbage collector won't know which task group was responsible for those allocations. And that is the conundrum. That is really where the discussion about precise measurements of heap allocations is complicated. This is what the code that's here is really an optimization that makes the heap allocation fast for small sizes, but that acceleration, the price of it is that the allocations are shared across Go routines running on the same processor, and they might belong to different task groups, and so it makes accounting difficult. So today we are not going to enter this bag of complexity. We're going to say, well, tiny allocations are complicated. Let's just not look at them right now. And we're going to focus on the large allocations for which we know that we're not sharing pages across Go routines and processors. And so I'm going to scroll down so that we're not in the small size. So which was the branch again? So if size is smaller than max size, and then we have here the tiny allocator and then the biggest allocator. So that was tiny allocator. Here we have the medium allocator, and then here we have the large allocator. So that is what we are going to focus on today. The alloc large function. So it's here. And then we have a couple of maintenance functions. Then we have an allocation here. And then we have a throw out of memory. Oh, that's interesting. What is throw? Well, it's good that this function throws when it's out of memory. Very good. Oh, I didn't know this. Out of memory. So do we get a panic with a throw? Is a throw a regular Go panic? Let's see. Where is throw being defined in the runtime system? It's certainly used in many places. So why am I looking at throw right now is because if this was a regular panic, then I will make a note of this for later. It's here. System stack, print fatal error, and then throwing, and then fatal throw. Unrecoverable runtime throw. Oh, okay, well, if it's unrecoverable, that is sad. Oh yes, okay, crash and exit. Oh, okay, so well, if it's unrecoverable, that's unrecoverable. Let's ignore it for a second. All right, so let's come back to the Go runtime, to the memory allocator. So we have here some statistics. So the large alloc thing is being incremented. Is that decremented anywhere later? Let's see. It doesn't look like it's being decremented anywhere. So, okay, so that's a general statistics counter, but sadly, it won't help us. All right, so page size plus page size smaller than size, and then it will round it to the next page. Okay, so we are actually allocating entire pages at a time. So page size, let's see where that is defined. Should be constant. I hope it's a constant. Yes, it is a constant. Cool. Then say heap life is being incremented. Ooh, heap life is nice. I like heap life because that means that this might get decremented somewhere. So heap life, hopefully gets decremented somewhere. Yeah, here. Okay, so this code knows how to decrease heap life at some point. That's great. Then we have a trace event if tracing is enabled. So tracing is a mechanism that prints out stuff on the standard error. It's not very clever. It doesn't really know how to send structured data anywhere. Like, it's not something that's really optimized for machine processing, but it has some purpose. GC blacken enable, GC controller.revise. I have no idea what that is. Controller state. What is the controller state? So revise, updates the assist ratio during the GC cycle to account for improved estimates. Okay. All right, so we're talking here about optimizations. Then put the large span in the mcentral swept list so that it's visible to the background sweeper. All right. And then we have a limit and heap bits for address s.base in span. Okay. So we need to look at, so S is the allocation that we're looking at. So Jordan is asking, good luck with this. Just listening in the background. I was poking at some of this on Friday as well to try and understand the memory map and GC state bitmaps. Yeah. So I'm actually, I did throw up the, throw away the towel already on the details. I just want to count large allocations today. And for this, I think that I actually don't need to understand too much. I just need to, well, just between quotes, I want to add a field to the spans that points back to the task group, or specifically to a counter in the task group, and have the GC, when it deallocates a span, decrements the counter with the size of the span. So that's what we're going to look at today. For smaller allocations, later. Too complicated otherwise. Where is the basic alloc function? Okay, what is mheap? Mheap. Come on. For somehow, I'm going to go and grab this. Or is mheap defined? Let's see. Mheap. Where's mheap? Come on. Oh, here. Okay, so it's an mheap. All right. That's what I needed. All right. So we are locating a new span of n pages. Cool. And then we have alloc span and clear Cool. And then we have here, need to provide physical page line stack allocations. Yep, I'm okay with that. Okay, so let's look at what's in the span. Okay. So what we're looking for here, it's actually exactly what we see in this file. It's a list of fields that are defined for every span. And so what we're going to do is to ensure that whenever those spans get allocated in the function, in the file we were looking at in a second ago, we are going to have a field added. So it's here, and then alloc to cache, alloc, and then is there a place where those fields get initialized? All right, half span, allocs need 0, init, I like init. All right, this is exactly what I wanted. So what we see here is the initialization of all the fields in the span. And so what we're going to add here is a pointer to a counter that needs to be decremented with the size of the allocation when the spans gets deallocated. Do we have a size field in here? Probably not, right? We have probably a base pointer and then maybe an end pointer, and that is used to do a decrease, or maybe there is something else entirely. So start address, a number of pages. Well, that's what it is. All right, so the size is defined by multiplying the number of pages by the size of a page. So I'm expecting something that looks like n pages times, oh, page shift. Oh, there you go. Oh, that was easy. And so there is a limit as well. That's okay. So that's the limit pointer, the end of the page. Cool. Number of bytes, free span, ampersand free. Exactly what we wanted. So n pages define the size. And I think we got exactly the function we needed to see. Actually, free span looks very, very promising. Oh, that is cool. That is pretty cool. So what is this function here? It's free span locked, all right. And so that is releasing the actual memory. And there are a couple of hey, accounting functions. That is cool. All right, so we have free manual and then free span, and both call free span locked. That sounds very promising. So we have here some general memory, xadd pages in use. So that's like for the total heap. That's decreasing the number of pages. Clear in use pages. All right, so we're okay with that. That is like just bookkeeping, and then statistics. So that's where we're going to do our little thing. Number of bytes. So heap in use gets decreased here. Yep. And then we have different modes pointer scalar bits in work buffs. All right, so this is good actually. This is a pretty much the stats that we needed to look at actually. So this is very good that we see that here. And we will want to have our accounting after this call here, because we want the accounting to be reflecting the memory after it's actually freed. Is that good enough? Nah, I'm afraid about this. Ideally, we want this accounting on the task group to occur after this is unlocked. Why do we care? It's because we are going to try to make accounting for data so that the counter is an accurate representation of memory usage. And so if we do a decrease of the counter before this call to free, then there is a little amount of time between the moment the counter gets decreased and the moment the memory gets actually deallocated. And during that time, the counter says that there is less memory used than what is actually used, and that's not great. And arguably, this entire block of memory statistics is not in the right place for the same reason. Let's see where this free is implemented. Page alloc, yeah. Simstack. Yeah, so that's where the memory is actually being released for further allocation. So this entire idea of decreasing the stats only later is odd. Doesn't really work for me. Let's put it this way. I'm going to mark this as a to do. The call to .free, and we actually do need also to make a note of this for later, because that needs to be further investigated. So possible heap stats bug. The stats in the heap stats get decreased during memory deallocation before the pages actually get back to the system under a loaded CPU usage. This could cause the stats to report less memory actually used, less memory used than what is still allocated. Possible resolution moves the call to h.pages.free above the stats update. That might need to be filed into the Go repository as an issue, in fact. Seems misplaced. The stats should be updated after the memory is effectively released. I'm not going to do anything about this right now because I don't want to create bugs that weren't there to start with. And I really want to focus on my experiments, which is to add a counter in the spans. And so we're just going to do this. h.pages in use. And so what we're going to do about this is the UN64. And so we're going to say big pages in use. All right. And there will be a pointer inside, say the stats update here. So what did we annotate? How did we annotate the changes here? So begin cockroach labs tweaks. That's what we did here. And then end cockroach labs tweaks. And then if s dot task group large heap usage is not nil, then in heap, is that a regular int 64 or a uint 64? Int 64. Byte delta of memory placed in the heap. Do I want a uint 64? All right. Like this. We obviously need to populate this pointer somewhere. It is here, and then we have a thing with tweaks. And span struct here. And then we have a task group large heap use. Where was it again? It's a pointer. Our usage. Okay. And we will need to erase this thing by default. Actually, oh, get G, I like this. Oh, we have a G. That means we can actually find our task group here. Ooh, that is going to be sweet. Alloc span. Almost n pages worth of memory. I love this. Okay, so that actually gives us much less work to do. Okay, so we're going to get there in a few minutes, but I do need a break for 2 minutes. So I'll be back in a sec. Thanks for dealing with this. See you in a bit. All right, back on stream. So we have this beautiful and very exciting alloc span structure, and it has even a G pointer. And if it has a G pointer, that means we can use that to extract the task group. And that is so cool. GP. I just don't remember whether it's the right G. So we're going to find that out actually with the test in a second. So there is a span. And at that point it's not shared, so there is no need to lock anything. And so we have the thing here, and that's where we do the statistics. What did we call it again? Big heap usage and address serif. Cool. All right. So this is basically tracking the ownership of this span to a task group, and we are now going to increment this. Seems that I don't need to do this, do I? It's going to say the cast is not necessary. I think the n bytes variable is already unsigned. Yeah, that seems about right. And so if I use xadd64, oh, apparently it is. All right, well, let's pretend we didn't see anything. And again, that's the same deal as earlier here. We see that the stats are being updated after, say, heap is being obtained from the physical allocators. That's also kind of a problem. Memory has been allocated. This means there is a span of time where we have unaccounted. And perhaps better to move the counting ahead of the actual allocation. And we're going to keep track of this here. Ditto on the allocation path. And then copy paste this. Possible resolution. Move the stats update above the page allocation. I mean, there are two phases, allocating a span and allocating the pages. And so there is something going on here, which is that the span is not actually allocated until the pages have been allocated. So basically the go runtime is saying, well, if I didn't get the pages, I might as well not allocate a span. But on the other hand, the entire Go allocator doesn't handle allocation errors in any case. So it's kind of moot to try to be clever about this. Like, if the allocation pages doesn't work, then it's going to fail with a non-recoverable panic. So we might as well get the span first, do the counting, then allocate physical memory, and then assign it. There is no error condition. So whatever. All right. But again, I said I'm not going to introduce bugs by moving the code around. Rather just try it out in this way with a little bit of misallocation, and then we're going to extract our metric. All right. All right. I think that's what it is. That's what it is. Let's try to build this. Build this Go runtime and see if it's able to track the big allocations. Moderately. All right. Good. I like this. Write barrier prohibited by caller. That's nice. Oh, that's a clever compiler. That is a clever compiler. I like this. So what it's telling us here is that the retrieval of this pointer in the task group CTX here is not allowed at this location. And the reason for this is that in Go, accessing the address of an object forces a write barrier, and we are not allowed to cause a compiler to create write barriers in the context of a heap allocation function. That's due to, I think, some assertion somewhere. That's okay. That's okay. That means we need to get our pointer in some different way. I'm kind of wondering, though, because there are other values that are being retrieved, and so can I avoid this? I can do it dirty. Or I can do it clean. I don't know. Do I want to do it dirty? I know how to do it dirty, but I'm not feeling comfortable with this. Or maybe, maybe that's it. Maybe that's, let's see. gp trace a page cache. Cool. And then there's another GP here. It was in runtime too. G-struct. And so we are looking at M. All right. And what does PTR do? Yeah, that's maybe what I need to do. All right, G uint PTR holds a Go routine pointer, but typed as uint PTR to bypass write barriers. That's exactly what I need. It's used in the Go buff Go routine state and in scheduling lists that are manipulated without a P. Yes. That is what I want. And then there is probably a regular P uint PTR for the same reason. And then unsafe pointer and PP P uint PTR. These are, yeah, okay. So do we have a clever PTR thing for uint 64s perhaps? Sorry. That would be fun. That would be fun. Is there, yeah, look at all these PTRs and save pointer. And save that pointer, return. So get G, no write barrier. That's also another thing we can do. All right. Yeah, so apparently I can't store. Yeah, so we're going to do a uint ptr thingy, so the same ways that this works. And so we are going to call it E64. E64. All right. All right. And then we need to ensure that the mspan here is a E64 uint ptr. All right. And then how does this work again? How is this called? All right. Task group like this. And so that's set like this. And then we have like this. Like this. This is going to be 0 because it's an integer data type now. And that looks fine. And this is a 0. All right, let's try this again. Failed again. Different reason. Oh yeah, wrong type in my cast. Here, so it's not a P. So the fact that those steps are succeeding informs us that the changes we made didn't break the heap allocation entirely, because all these commands are using the Go compiler containing the changes. So if there was a problem, we would see it here. Now we're going to modify the CockroachDB source code that is using those values. Oops. To extract those new things. And how did it called? How did we call it? Large heap usage bytes. This needs to be modified in the server pb file, and we should not remember where it is. Server pb proto, which one was it? Admin.proto, status.proto. Yep. Here. And so we are going to add this here. Large bytes. Did we call it large bytes just a second ago? I think we did. Did we not? Large bytes, yes. The number of bytes allocated in the Go large heap for all Go routines marked associated to that session. Yep, that seems to be right. And then there is a CRDB internal here that is going to be added here. And that is large bytes. It's a new column, and because it's a new column, we need to declare it. And it is here. All right. The number of bytes used in the large heap gateway node. All right. And let's build this now. So in this test, we're verifying that the CockroachDB can run, that it doesn't crash with some kind of Go heap allocation internal error or something, basically that we didn't really introduce a bug inside the heap allocator. But when we're going to look at the large bytes usage, we are likely going to see 0. I'm predicting it's going to be 0. And the reason is that in CockroachDB, it's not common. I don't think that SQL sessions or SQL queries in most cases will need large allocations. And so the amount of M-spans that are going to be built on behalf of a individual Cockroach query is likely to be 0. So if we see 0 in the table, don't panic. All right, I made a mistake in the SQL syntax. Yay. That should really be checked by a linter, in my opinion. Let's build this again. So if we, assuming this succeeds, if we see an error, it's not going to be, we hope it's not going to be in the Go runtime, in the garbage collector or the heap collector. Let's see. All right, so process seems to work. Still runs queries. Didn't break CockroachDB too much. And node sessions. All right, so what I said earlier, Jordan says, try something like select some length of S from T with a big S column. Yes, thank you for your suggestion. Like creating something large in memory. There is a slightly better trick, because I believe we have a generate series. And so I like to do this. Who? Why can I not use the column reference here? That's odd. Oh, whatever. All right, so I have here a large query, a large value. I'm going to make it even bigger. Is that big enough for a page? Probably not. Make it bigger, and then length. That's maybe extreme. That might actually fail with the memory allocation panic. Yeah, but that's good. Anyway, let's come back to our node station table, and the counter is still 0, which is not surprising at this point, because by the time this error is reached, of course, the thing has been decreased to 0. So what if we were temporarily to remove the decrease part of the code? So basically, just for testing, we're not going to decrease the value. We're going to just keep it increasing forever and then hope for the best. This idea here, what is a large byte size threshold? Say again, which size threshold? Oh, you mean at which point does it start using the large heap? Yes, that's a good question. Let's find that out. It's in the small size. Max small size. What is max small size? Apparently that would be 32 kilobytes. So hopefully we should see it in our test. Hopefully. But there is a little thing, like it's possible that we are not going to see anything, and I'm going to explain why in a second. Like if this doesn't succeed, I have a theory, and that's the same thing we encounter the first time around when we were doing CPU accounting. We were not looking at the right Go routine. The idea being that when the allocation starts, it switches the Go routine context to the system context. Because it doesn't want to use the Go routine stack for performing the heap allocation. And so if my Go routine pointer is wrong, then the task group pointer is not going to be defined, and then there is nothing to see. So we'll see. All right, so we said, let's make a large allocation, and then look at this. And it's still 0. Yeah, it doesn't get increased. So that tells us a little bit that we don't have any task context here defined. So that's the same kind of situation we encountered the first time around back in the days. And so what we're going to do here, we're going to add some debug prints in the Go runtime. Basically here, if this is defined, we want this to be printed out. Right? Print. Okay. Print alloc in task group. I think print already prints a new line at the end. Because if that never gets printed, then we know that we are not, in fact, setting this properly. So that's why I'm referring to the case we had before. This GP here back in the days was actually not the right GP. So we have a GP here, and then we have a get G. So the _G is the current, like in memory, the system G, if you will, and GP is the one from where the allocation is coming from. And this function here we're looking at from the beginning, alloc span, is called from, say, a context where we are not in the same G anymore. And that means we might need to pass some pointer through with arguments. We'll see. Maybe it's not needed, maybe it is. So what I see here in any case is that I didn't see my print anywhere, so that seems to be okay. I need to rebuild with custom Go runtime. And in ideal world, when I start the cockroach binary, I would start to see prints in the standard error. So I probably need to add some logging flag for this. to see them interleaved. We'll see. Cool. All right, so demo empty log stray hairs enable false. All right. Yeah, so I'm not seeing my my big heap here. What would be another way to get a lot of data in one go in this? Oh, my internet had a little break. Sorry about the little upload pause. What would be another way to get a lot of data inside CockroachDB in one go? Let's see. Is there a multiplication, like a string multiplication function that I could use? Or maybe paste a big amount of data in one go? Maybe? What would be the good way? Yeah, I'm not seeing. I'm going to start with a CockroachDB server instead. And then like this, and then cockroach secure, and then make some big thing, and I don't see any print here, so our code here doesn't get called. All right, so we know at least that the G could make a small test program to play with to avoid long CRDB recompile times. Yeah, you're very right. I should absolutely be doing this. Maybe it's time to do this, right? Did I not have a test program that was doing this earlier? Yeah, I had it here. That was our test program. Let's do this moving forward. Much better. Thank you, Jordan, for your suggestion. I should have done that from the beginning. All right, so let's make a task group. I don't remember how this goes. In fact, let's executor group. Right. So all right. Then what do we do with this? We're going to retrieve the metrics as is done in the other file. Right. Right. And so I'm going to say get metrics Then I would say this. Yep. Okay, that's okay. I think. Except that I didn't do set internal task group properly, so that doesn't seem right. So let's look at how this works. Set internal task group. So creates a new task group and attaches it to the current Go routine. It is inherited by future children Go routines. Top level Go routines that have not been set to task group share a global default task group. All right, so that's what we wanted. All right, so that's good. Let's make our test function run in a sub Go routine. Go test. Wait, I think that sync. Right. Why do we use a separate Go routine here is because I'm not trusting that the main function runs into a Go routine that we can annotate. But anyway. Cool. Okay, so those metrics don't seem to be taking too much time, do they? So we need to do some useful work here. Something that takes time. Better. Cool. All right, so that seems to work. One CPU slice, and the second slice is, say, CPU time in nanoseconds. Why do I get only 8,000 nanoseconds, like 1 microsecond? Oh, it's because, of course, sleep doesn't take any time on the in the Go routine. So that's like super quick. Why does println doesn't take anything? I don't know, actually. That's actually kind of confusing. But I'm kind of happy about the fact that we have our counters working, and so here we are going to allocate something big, and then print something about it later. Let's make it big, like 100,000, and then maybe like this, and then oh, I know what we're going to do. Cool. Cool. All right, so there is a big chunk of memory allocated, and we didn't see our message. So that means that either the Go routine is wrong, or we didn't modify the files in the right place. So just for the sake of testing, we're going to do some absolutely obnoxious large amount of debugging. And we're going to do this by printing out, by showing basically the user, say, the address of the coroutine. Oh, getg.m.curg. Oh. Oh. That's what I need, I think. Oh. Ah. Haha. Ha ha ha. I forgot about this little detail. The current coroutine is accessible via the M pointer. That's better. Oh, that is so much better. Segmentation fault. That's great. That is very good. We got a segmentation fault. Isn't that great? Brilliant. Why do we get segmentation fault is yet to be determined, but that's more like it. That means at least that there is something going on here. So where did it happen? That is the question. So go bootstrap install gc flags cm config signal segmentation fault. Is that going to be reproducible? Exactly in the right place? I hope so. There is nothing like failure to find out problems. Yay. Okay, so we can... Yes, that is good. Now we're going to trace this of GDB. Yay, that is good. Okay, that's good. That is also good. That is not good. All right, so the curve is not being set in this context. All right, I don't mind. Okay, status quo CTX is not being set. Okay, well, never mind. That was not the right approach. But maybe it was. Maybe we just need to set the curve somewhere. All right, at least that explains. I'm going to come back to malloc.gc and see if I have any information in this function about the current go routine, and to see if I can fish that out. So we have the getg is here. Oops. So where is curg being defined? I think it's defined the moment where we have a preemption, but the malloc.gc function is not during the preemption. It's not in the scheduler. So that's why the getg might actually be the right one. I actually want an accessor. So that is good. Get PID. I actually want to have just for testing purposes. Oh, look at this. we have, oh, I like this code. Look at this. I like this. I like this much more. And then we're also going to print out the things. And then like this. And then we are going to report what we are doing here. All right. Magicking is saying this G between the square brackets is an allocation or an assignation, curly braces here. You mean here? Is that right? I think that's what you mean. So what this is doing, all right, so this is actually digging up some knowledge I think I gathered last time I was looking into this, but I think I also forgot a little bit about it. So my explanation might not be accurate. Take it with a grain of salt. We need to verify this later on. After we do the experiments, suppose the experiment is successful, we'll need to check all this knowledge and actually ascertain it. But preliminarily, my understanding is the following. Depending on whether an allocation is taking place inside the Go runtime by the scheduler itself, or inside some other component that is running outside of the program goroutines, we have a goroutine struct that is kind of separate from all the M's, all the P's, and so on. And that means that it doesn't have a back reference from curg into itself. Whereas a program goroutine will have such a reference. And so what this piece of code is doing here is the same that is happening in the malloc function here. I'm going to show you this in a second. Here. It's the same as here. Like charge the current user G for this allocation. So the user G might be either the get G directly or the one at curg here. And so that the difference here is when it's like goroutine run for the runtime versus goroutine runs for the program, like coming from the program. And so if this malloc function is doing this, that means that we should be doing it here as well. So that's what I'm just figuring out. But in addition of figuring that out, I also decided to add some copious print statements. It's not the same code, are you saying? Why is it not the same code? What's different? Oh, thank you. I think the Go compiler would have complained in my face. It would have said that the this_g variable inside the braces was unused. Let's try it. I'm going to show you actually. I think it's cool. Let's build this. It's going to complain. It says the variable is not being used, and that's invalid Go. See? No. Oh, never mind. What is this? Who? Give me a sec. What's going on here? Wait. Why is it broken? 1313 here. Oh, separate problem. Cannot convert to type uint ptr. by pointer. All right. All right. And same here. So again, I remember what you said about this, and I think the Go compiler is going to give us an error message about this. Proc API 29. Here. And then here. I hope it's going to tell me that the variable is not used. See, I told you, this is G declare but not use. So thank you for fixing it, but the Go compiler would have told me. Yep, there we go. So let's move forward. Yay, look at this. Beautiful. Why does it use task groups, in fact? All these prints you see here, not expected. So we're going to have this, and then a new line. Oh, maybe print exists in a println variant. That would be nice. But we're not expecting task groups being defined for the... Oh, the top level Go routines has a default task group. We had that choice made a while ago. Yes, this is nice. All right, so what we see here is that all these Go routine pointers are like printed in decimal. They're all attached to the default task group. And so here we're seeing out different processes. So all the processes will have a different task group pointer. That's completely okay. I'm comfortable with this. All these prints, of course, are slowing down our program a lot. But it's okay. It's okay. It's okay. Now we can run this. And now we are talking. Look at this. We have achieved. And so the value is not getting back to 0, obviously, because as we discussed before, we remove for testing purposes. We will remove the decrement back to 0. All right, so I'm going to remove this printf debugging a little bit for the time being because it's very verbose and I'm kind of confident this kind of works now. Here. And then rebuild this. Cool. So we see here that before this point we had one page allocator. So the pages are, I think, either 4 or 8K. And so when in our test program here, when we arrive to this between those two lines, we already have an allocation ongoing, and it's going to be because of this map here, I think. Either this map or the work done inside this function that is happening after we have set the task group here. So all this allocation, this retrieval metrics is allocating some memory. And then we have this additional allocation that's going to come in the after thing. And then that memory is being freed, really. It's not needed anymore. And so let's print this here. And then we're going to have here our print going on here. And what we want to do after this, we want to wait for a while. To see whether the heap collector, the garbage collector, runs. And hopefully we will see the value decrease. And then we will know we have achieved success. So like this is an empty loop, so it's not going to work very well. So I need to have a time.sleep second here to see the value, because at this point, the value is still in scope. So we need to get that in a different function. Cool. Why do I need the first function? Because I need the mymem pointer to go out of scope. Otherwise, there is no reason for it to be deallocated. All right. Is there a trick to force the heap collector to run? I think there is maybe a run gc, force gc, runtime.gc. Oh, well, that is cool. Yep, it did something. It did something. It did something. We saw the value decrease. That is so cool. So cool. I don't exactly know why I'm not seeing this big value here. Decrease. Also, I probably want this to be at the end. So we want the value before the decrease first time. And then like this. Maybe that's going to clarify basically what we're doing. That is going to clarify what we're doing. Look at this. Oh, sweet, sweet. Look at this. Look at this. Our memory that we just allocated for array is accounted for. Like, that's not surprising. We just allocated 8 megabytes. So because like 1,000,000 times 8 bytes, like the integers are 8 bytes, is 8 megabytes. And then we run the GC, and those 8 megabytes go away. And what's left over is some allocations for the small heap for the task group. Because as we discussed at the very beginning of this session, we are not accounting, we're not going to be able to fine-grain deallocate the M-spans of the small heap. So that is actually, that's actually kind of, there is a little brokenness here. All right, so there is a shortcoming. But like what was happening basically is that we're only accurate on the large allocations. And for small allocations, all the solution is kind of not great. So what's currently happening, and maybe we should actually fix this in this stream just to make the example more powerful. What's happening today is that when a span gets allocated in a task group for the small heap, that's going to be reused with other Go routines on the current P. The code we added to create, to increase the counter, to annotate the task group for the span, and to increase the counter in the task group is going to be executed as well. And so the mistake we're making here is that we should really only do the increment, the assignment of the task group pointer and the increment for the stats in the case of a large allocation. And today we're doing it for also small allocations. And that's not the scope today. Like, we knew from the very beginning that the small allocations would not get accounted properly. So that's what we need to fix now. Like, we need to exclude the small allocations from our story. And so what we did here to make it work, we put the increment in a common function that is allocated, that is used for both say small heap and the large heap, which is allocspan. Obviously allocspan is used in many places, and we don't want that. So we have allocspan for alloc. That's big alloc. And then we also have alloc manual here. I don't know exactly what I'm doing. Allocspan. Well, my point remains. We need to be a bit more focused on the malloc function here to only do this accounting when we are looking at a small allocation. All right, so where is the small allocation being handled? So we have here a small allocation, and then make span class. Yes, that's basically what we don't want, and then alloc large. So it's in alloc large that we want to do something. Here, yeah, yes, that's where we were. And so here we had a make span class, trace heap, full swap. Where was the alloc large going on? Allocation span for a large object. Here. That's the one. Cool. So what we're going to do here is this, and then we take this, and then we put it here. And now we are only looking at large allocations. And so hopefully our test will become more convincing because it will be more focused. All right. And define GP. Yeah. Of course, because I'm not in the right place. Like this. All right. And bytes. Ooh. Yep. Oh, I forgot to update the link for today at the bottom of the screen. That is completely inaccurate. That was from last week. What is this issue we're working on today? It's this one. Off we go. Cool. All right, so let's run our program again. That is not good. It's not completely bad either, right? I mean, like, it's allocating 16 megabytes. And then decrease here. All right. What are these allocations about? All right. I don't mind. Better. And probably the some part of the problem is that printf is allocating global memory. So we're going to do something like this. Didn't really help. I don't actually know exactly what is the where we see allocations going on, but at least like we're seeing the 8 megabytes of our large allocation being decreased properly. So there is this 8 megabytes going on here, which I find a little bit suspicious, but it is what we did. It is what we did, and that is what was allocated after all. So yeah, the number of bytes being allocated is n pages times page size. So we are looking here at an allocation for that task group that seems to be done to be complete. 1 million bytes times 8, so that's 8 megabytes. Yeah, not surprising. Why do we have 8 more megabytes remaining afterwards? Like we have 2 times 8 megabytes being allocated. Oh, the stack, I think. Yeah, let's call foo the first time here to allocate the stack, to pre-allocate the stack. Aha. Well, that is helping. That is helping. We see the stacks being allocated. Ooh, and that tells me a little bit more about what to test here. We're going to extract the code that does the allocation outside of this. Yeah, let's do this. Let's do this. We're allocating this here. And because the task group, all the Go routines created from that task group are going to inherit the task group, obviously. That's what we were interested in doing. And then we're going to do the work here. And then we are going to let the Go routine exit and then do the just GC. So this way we are going to ensure that the stack allocation for that Go routine gets accounted for and then deallocated. Better, somewhat better. All right, so this is cool. We have exactly 1,000 pages being allocated here, and that's not completely surprising. And the reason for this is probably because we have 1,000 pages that have arrived in the middle heap from the large alloc function. So alloc large is probably not called just in one place. span malloc gc. Yeah, malloc gc is being called in multiple places, isn't it? New array. Yeah, so there is something going on in between. In between those calls somewhere. I don't know exactly, but we do have our memory, our large heap allocation counter. So like here in this particular case, and maybe if I make this smaller array, so I want this to be larger than 32k, so I need to have 32 divided by 4. I need to have 8,000 items and 1. And that should be sufficient to bring it above the threshold. Yep. Oh, that worked. Huh. So apparently our array is allocated 2 times or something like this. Yeah, that's good enough. I like to see this. This is very good. This is very, very good. I think we achieved success twice over today. That is very good. That is actually not so good. Wait a second. After GC, so we have 40k here. Then after GC, we have actually more memory allocated, and then it decreases at 90,000. That's odd. But I don't mind this. We can accept this. I'm not exactly sure what it's due to, but I don't mind. Let's build CockroachDB again. And see what CockroachDB says about this. All right. So node sessions had some memory allocated here. Oh, and it decreases. And then it decreases again. So we see 1 megabyte allocated and it increases forever. And all this increase is probably okay. It has to do something with the fact that we have like ongoing allocations, and then it decreases when the garbage collector runs. So we have here a session going to 1 plus 1.5 megabytes, 1.6 megabytes, and then back to 500k. So that's more or less the behavior we wanted. That's more or less what behavior we wanted. I'm so happy. I'm so happy when experiments go well. All right, let's talk about committing code. All right, so we're going to remove our debug prints that we had here. We're also going to remove the getGP thing because we ended up not needing it at all. All right, so we're going to add the comment about these things because that's a separate thing that and then in the yes, that's okay. In the heap, here. All right. Yes, here. Send here, this, send this, and send this. All right, let's go back. So this is this. We're going to have that a bit later. So these comments here, how did we call our commits? Remind ourselves about possible cache contention. And now we are going to have this commit here. Yep. That sounds fine. And how did we call this? Measure per task group large heap usage. Cool. Push this upstream. And then doing some commit in CockroachDB as well. Here. Okay, so we just simply, I think, verifying that this regenerates large bytes. Con executor. Let's go. And then we're going to modify. And then, all right, collect access. Cool. I think this is fine, right? It's not regenerating any file, okay. Then we push this. And now we have this. We have a PR that does things, and we are going to change the RFC accordingly. We want to explain in the RFC what happened today. For this, I have a separate working directory. Oh, stupid me. I could just say this. Much easier. Who? Oh, okay. Okay. I was already there. All right, so let's go and modify this RFC then. Docs, RFC, task groups. Cool. That will be more or less the end of the stream once we have this text updated. Task group abstraction. Metrics by application code. Task group abstraction, CPU scheduler ticks. We did that before. Precise CPU time utilization. We did that before. Heap usage. Context. All right. We can tweak the heap allocator as follows. Large allocation tags with pointers, task groups, ETX. Yes, large CM span for large. Okay. All right. We had that discussion, custom allocators, and we'll see. Okay, so we need to have a section that explains. See proof of concept below. Right. So there is an explanation about the proof of concept. Example metrics. Heap usage. Where do we not want to put our proof of concept? Here, I think. Allocations, see go heap allocator, allocates, dedicates entire M spans to null unit of accounting to each allocation. And allocation is considered large when it is 32 kilobyte. C, so how was the name again? Small size. What was it? Size classes here. All right. Because CM spans are dedicated, we can do a precise accounting as described below. B, all right. How to achieve this, and then we're going to describe what we did in the current time. In what was it, mcache, increment, add a new large heap use counter in the task group struct. The task group counter if a task group is defined. What was the other part? In the free function. Where was it? Where is it being decreased? Here. In heap free span locked. Also store a pointer to the counter, the task group inside the M span. If a counter pointer is present in the M span, decrease it by the size of the allocation. All right. We place the increase in alloc large and not alloc span, because the latter is also used for small allocations for pre-populating M spans, small heap, and we do not yet know how to do bookkeeping. And this proof of concept does not is limited. See discussion above about the complexities. All right. When this is achieved, we can expose the new counter via the metrics. the API, for example, in executor.go. Where was it? This is demonstrated in the custom Go runtime at and the PR at this one. All right. Cool. We have modified this. Do we need to discuss the rest? Maybe we will need to process comments from most people, but whatever. Markdown, doc, refresh. Off we go. And then there is a proof of concept. Present. Cool. All right. Yep. 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 Okay, so let's commit this and then notify people. Oopsie. Modify meant push. And then there should be a new section here. Here. And then I'm going to add a comment here. I was able to add precise tracking for large allocations. See new explanatory section here. And if we look at cockroachdb with this bash in place, we see the large byte column in CRDB internal dr-knz sessions periodically increase and decrease in proportion with the activities of the SQL session as expected. Cool. There is a discussion that will come with this, and that will be whether that's sufficient for memory tracking in CockroachDB, or are we seeing a lot of allocations happening in the small heap? We don't know that yet. We will need to experiment to figure it out. We'll see. Anyway, so today we have made some patches to the Go runtime and added precise tracking for memory usage, in addition to the ability we had already to track CPU time. So we're going the right way, I would say. This is good. I'm pretty happy about this. And thank you for Jordan for suggesting to run a small unit test, like small manual test with separate code. So I had accelerated the process a little bit. And I think that now that we've experienced a lot of success with this, as the next time we're going to work on this project, we need to create a more robust API, something that works even for people who don't use the custom Go runtime. I mean, not that it works, but like that we don't want to have Go code in CockroachDB that doesn't build at all unless the patches are applied. We want instead to have something like, oh, you're going to have degraded experience if you don't use our patches, because we still want people to be able to run with the basic Go runtime. So that's going to be a discussion for next time. But for today, let's say it was pretty rewarding. So good experiment, good stuff. And thank you for riding along. I hope that by next time we all gather and work on this project again, there will be more exciting news of how we're going to plan using this, and maybe we're going to look at performance impact and things like this. Anyway, so thank you again for tuning in today. This was a good day, and I hope you enjoyed it as much as I did. Have a very good week, and we will talk again next week. Have a very good day. Thanks, Magic King. See you. Bye.